We're going to start out chapter 11 by talking about inverse functions. And before we get to our first definition of one-to-one function, I'm going to refresh our memories with what a definition of a function is. So the definition of a function is when each x value corresponds to only one y value. If you remember what that meant is we looked for duplicates of x, because if we saw duplicates of x, that meant that it went to different y values and then it wouldn't meet the criteria. We also did this by using the vertical line test. If we look at the definition of one-to-one function, you will see that it says each x value corresponds to only one y value, and each y value corresponds to only one x value. And so it's very similar to a function, except it has this added part. So not only are we looking for duplicates of x, but now we're looking for duplicates of y, because it needs to have a one-to-one correspondence. So we have two examples right here in the boxes, and we have four domains that are being assigned to ranges. And what you're going to do basically is you're going to look at your domain, and if we look at the domain, there are no duplicates of the x. So that tells us it is a function. And then we'll go to the ranges, which is the y. And there's no duplicates of the y. Therefore, it is a one-to-one correspondence. And just to kind of re-emphasize, it has to be a function before you can make it a one-to-one. So if there is duplicates in the x, then automatically it cannot be one-to-one as well. So this case, it is a function, and it is a one-to-one function at that. So then let's look at the next example. We look at the x's. There are no duplicates in the x's, so it is a function. But if we look at the ranges, there's duplicates in the range, and they're being assigned to two different x's. Therefore, this is not a one-to-one function. If a function is one-to-one, it can have what we call an inverse function. And that inverse function occurs, again, only with one-to-one, and it's written with the notation f of -1. And it's a set of all ordered pairs of the form yx, where x, y belongs to the function. Basically, you're switching the x and the y's around. So the domains become the ranges, and the ranges become the domain. So again, all you're doing is swapping those two things. One other thing that we gotta notice is that the horizontal line test. The horizontal line test can be determined when you look at a graph to test for one-to-one. Again, you want to use the vertical line test first to determine if it's a function, because if it's not a function, it can't even be a one-to-one. So what we're going to be doing for most of this, in example number 1, is we're going to be looking at these, and these are all function, and we're going to determine if they are one-to-one. So again, we can tell this is one-to-one by looking at the x's. All the x's are different. And then we look at the y's. We have 5, 6, 8, and 7. So all of the y's are different. So this is a one-to-one function. So we can create an inverse. To create an inverse, especially with a relation like this, all you have to do is switch the x and the y's. So instead of 2, 5, I now have 5, 2. Instead of 3, 6, I have 6, 3, and so on. And that's all you have to do with coordinate points. So now if we look at letter B, we'll look at the x's. Again, their functions are all different. But if we look at the y's, you'll see that there are duplicates in the y's. So even though it's a function, it is not a one-to-one function. And because it's not a one-to-one function, it cannot be an inverse. Letter C, you'll notice it's not just coordinate points anymore, but it's an actual function graph. If we think about what that looks like, it would start at -4 for the y-intercept, and it has a slope of 3, so it's going to be a linear line. And what you would do is you would just start with a vertical line and basically just scan it across the graph. You see how it only hits once? So that tells you it's a function, but now let's make it horizontal. I'm going to scan it down, and because it only hits at most once, this is a one-to-one function. So there aren't any specific coordinate points. Well, there are, but there's millions of them. So how do we actually write the inverse? Well, we do what we did in the other ones. We swap x and y. What we're going to do is we're going to make the f of x y, because that's really kind of what it stands for. So y equals 3x minus 4. We're going to exchange the x and the y. So x equals 3y minus 4. And now I'm just going to solve for the y. X plus 4 equals 3y. We can divide by 3. So the function, the inverse function of x equals x plus 4 over 3. Letter D, same sort of thing. If I look at the function, and if I think about what that graph looks like, it looks like this. It passes both the vertical and horizontal line test, so it is a one-to-one function. So what we're going to do is I'm going to rewrite this using y, and then swap the x and the y's, and then solve for the new y. X minus 1 equals y cubed, and then I take the cube root. And again, the notation for this will be f of -1 . Letter E gives us the function of x equals the quantity x minus 3 squared. So based on our patterns of graphs, we know this is going to be a parabola, and it's going to be shifted to the right 3. So 1, 2, 3, and it's going to look like this. It passes the vertical line test, but as you can see, it fails the horizontal line test. So this is not one-to-one. And again, if it's not one-to-one, you cannot create an inverse. F, if you take a look at it, it fails the fails the horizontal line test. So it's not a one-to-one function. E is though, or does pass both, so this is a one-to-one function. What I would do in this case if I actually wanted to write an equation is I would actually calculate what the y-intercept is and the slope. And once I have that, I would create, y equals mx plus b. And then I can just do that pattern once you have specific points for that. What I want to do for the last couple of minutes is I want to take a look at what the graph looks like of inverse functions. So the first one says to graph the quantity x minus 2 to the third power and y equals x to the 1/3 plus 2. So I want to go to Desmos to show you that real quick. So here are the two graphs. Okay, I would kind of make a sketch of this on your paper. And hopefully you can see kind of the pattern that's happening here with the blue and then here with the red. And you'll notice that they cross right there. And there's kind of this symmetry that happens with both of them. Pause it for a second and think about where that symmetry happens and see if you can kind of think about what that actual line is. So that line is y equals x. If we take a look at it, you can see it kind of split down the middle. And there's this great symmetry that happens. This distance is the same on either side. One thing I want to point out, like we mentioned earlier, this point is 0, 2, but you'll find this here at 2, 0, and same with other points. This point right here is 2, maybe 3.25, but then at 3.25, comma 2, we'll find that there. So, there's all this x, y that happens, and that's why the line is the way it is. Y equals x, because you are just switching the two variables. And we're going to finish up this lesson just showing you how you would actually graph the inverse function. So if this was a function right here, I would get as many points, I'd plot as many points as I can along the line, and I'd write them down. So this is 2, 1. This is 1, -1. The next one is 0, -2, and finally -1, -3. And all I would do is swap them. I'd get 1, 2, -1, 1, -2, 0, -3, -1. And I'd start plotting those. So 1, 2, -1, 1, -2, 0, -3, -1. And I would just kind of try to create this symmetry that we see happening with the other one. And what you should hopefully see, you see the symmetry happen right along this line y equals x. Hopefully those distances are all going to be matched up.